Hello, my name is Naveen Baksani, and this is my lab report on constant velocity. In this lab, I will be defining constant velocity and its connection to Newtonian physics, testing for constant velocity using a real-life example. Now, Honda Pilot SE was recorded moving at a constant velocity, and the motion was analyzed using Tracker, and then computationally modeled through VIDLE, a software run by Python. After comparing my experiment's results to the computer model, I'll be able to determine if the car was in fact moving at constant velocity in the designated time period and that there was in fact no net force. Two main principles that are displayed in this lab: Newton's first law and Newton's second law. Newton's first law of motion, sometimes referred to as the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same velocity unless acted upon by a non-zero net force. One key point to note is that velocity is a vector, meaning that it has multiple components. In this case, velocity has two components, speed and direction. Velocity is defined as the change in position over time. Newton's second law of motion states that force is equal to mass times acceleration, which is the change in velocity over time. But by deriving further and rearranging variables, we reach this final equation and get V final is equal to V initial plus the net force over mass times delta t. Looking at this equation, we know that if the F net over m times delta t component is equal to 0, then final velocity is equal to the initial velocity. Since the change in time and mass have to be non-zero values, net force must be 0 for that whole component of the equation to equal 0, and for there to be no change in velocity, aka constant velocity. I took a video of my mom driving her car at what seemed like constant velocity. In this example, the car is the system and everything else around is the surroundings. According to Newton's first law, the car should stay at the same speed, going in the same direction unless acted upon by a non-zero net force. I graphed the points on tracker, which you can see in the top right of this image. The graph looked mostly linear, suggesting constant velocity. Some of the discrepancy may have come about due to a pattern that was observed. Every 5 frames or so, there will be an elongated frame, leading to an impression of increased velocity at that point. We will see how this affects our final results later. In this graph, the x-axis matters, with the y-axis and the z-axis irrelevant. Also, the right direction was chosen as the positive x direction. In this table below on the bottom right, there is some very important information as well, because it gives 1 position and 2 time. The time changes from 0 to 0.891 seconds, and the position changes from negative 0.0278 to negative 4.60 meters. This data is then plugged into the skeleton Python code provided along with a few other key points. The first addition to the code was shown here with the car's mass, which is found online. Next, we added the car's position, which is taken directly from tracker in the first line. And then next was the car's velocity, which was calculated by looking at the first 2 points of the tracker data and finding the change in position over the change in time, as shown here, to produce negative 3.79 in the x direction. As you can see right here, the while loop. This while loop is an iterative function that keeps running until 0.891 seconds, the final time. F net is equal to 0, which shows no net forces. And this next line is essentially the Newton's second law rewritten in terms of assignments. And the last line right here is showing the change of position using the above line for the progression of the time period. The module produces this. And here's the graph. When comparing the graphs of the model versus the experiment, there's a pretty big amount of discrepancy. This is especially seen by the fact that the observed has a displacement almost 1.2 greater than the expected, which is 35% greater than expected. The circled points are the troubled points. These are the points where it seems like the video has a slower shutter speed and has captured more video per frame. At first it didn't seem much of an issue, but at each trouble point the slope, change in x over the change in time, was dramatically changed, altering the velocity of a car, making the car seem to be accelerating rather than moving at a constant velocity. Now, for the questions related to the lab, the first question asks what would happen if the axes were flipped. If the axes were flipped, the car would be moving in the positive x direction rather than the negative. The slope, the velocity, would also change. Rather than producing a graph moving down and to the right, suggesting a negative slope, the graph would be up and to the right, suggesting a positive slope. When last question asks, is it possible to determine the types of forces and how many forces are occurring? The answer is no. Just from observation, it's not possible to determine how many pushes or pulls, or types of pushes and pulls that are acting on the system to produce a zero net force. We're not able to identify the individual forces. Instead, all we know is that since there is a constant velocity, the net force must be zero, according to Newton's second law.